Hello everyone, welcome to this lecture on electromagnetic induction. So this is your first class in electromagnetic induction, and in this case this is the syllabus. So you have got Faraday's law, the Lenz's law, self-inductance and mutual inductance, reciprocity theorem, energy stored in a magnetic field, introduction to the Maxwell's equations, and charge conservation and displacement current. So these are the topics that we have to discuss in this particular unit. So in today's lecture, we will talk about the Faraday's laws. So Faraday's law basically may be considered as one of the fundamental laws of electromagnetic theory. In order to discuss Faraday's law, let's consider this experiment. What Faraday observed, whenever you consider a coil, this is a coil basically, and with this there is a galvanometer connected here. So galvanometer is a device which shows whenever there is a current passing through the galvanometer, it shows deflection. Now based upon the direction of the current, galvanometer shows either a positive deflection or a negative deflection. So what Faraday observed, he took a magnet, sort of a bar magnet. So this is a bar magnet which has got two ends or two poles. One is a northern pole, another is a southern pole. So if you put this bar magnet in a static condition or stationary condition, as has been shown in this figure, we see no deflection of the needle which is attached to this coil, or basically the galvanometer. However, when you shift this magnet rightward, that means towards the coil, we see that a current is produced and there is a rightward deflection of the galvanometer. Quite similarly, whenever you have got the faster movement of the magnet towards the coil, the galvanometer shows even further deflection. So that means what? Whenever you move the magnet faster towards this coil, or the velocity of the magnet is high towards the coil, in that case the galvanometer shows much more deflection. So galvanometer shows much more deflection means what? That current flowing through this coil is also high. Alright? Quite contrary to this, whenever you take this magnet away from the coil, then also the galvanometer shows a deflection, but this time the deflection is in opposite direction. That means current flowing through the coil is in opposite direction. Previously coil has set up a current which is in this particular direction, and now the current is in opposite direction to the previous one. So what we have observed, or what we have learned from this particular experiment, that whenever we take a magnet, if the magnet is at rest with respect to the coil, there is no deflection in the galvanometer, or current flowing through the galvanometer is zero. And whenever the magnet is moving towards the coil, the current is established into the coil, and the current increases with the velocity of the magnet. Means greater the velocity of the magnet, greater is the amount of current produced in the coil. If you move the magnet in the opposite direction, in that case current flowing through the circuit is also in the opposite direction. So why actually it happens so? Based upon this experiment, Faraday devised certain kinds of laws. Basically there are two statements of the law, I will come to that. But before that, why does it happen? So what actually happens whenever you move the magnet? Suppose this is a area, some kind of an area, cross-sectional area, let's say. It's a cross-sectional area. Through which the magnetic field lines are passing. This is a northern side, this is southern side. So magnetic field lines will come out of the northern side and will get in to the magnet through the southern side. So whenever, suppose this coil is here, so the number of field lines crossing the coil is more. So for example, you have got, it's less. Suppose you have got only 1, 2, 3, 4 numbers of magnetic field lines. So this is 1, 2, 3 or 4 numbers of magnetic field lines are crossing this. Now what happens whenever you bring this magnet closer to this coil? Or in order to say that, let us say that the coil is being brought closer to the magnet. So in that case, what will happen? Let us draw this coil somewhere near to the magnet. What we will observe? This is the diameter of the coil, and now see the entire, almost there are 6 magnetic lines, then 6 out of 6 are now passing through this coil. So that means what, whenever the magnet moves closer to the coil, the number of field lines crossing the area of the cross-sectional area of the coil is more. So that means what, the change in flux is more. Why change in flux is more? The reason is that magnetic flux is actually defined as the dot product of magnetic field and the area, or rather we sometimes call it to be phi, the magnetic field line, a magnetic flux, that is equal to B ds cos of theta, where theta is the angle between the magnetic field and the area cross section. So flux per unit area is something called the magnetic field. So that is the reason why whenever you have got a cross-sectional area through which the more numbers of magnetic field lines are crossing, that naturally increases the phi with respect to time. So in case of the previous experiment, the same thing was happening. Whenever you are bringing this magnet close to this coil, the number of field lines crossing through this coil was increasing, which was resulting in the change in phi, that means flux. So that means there is a term which is called d phi dt which exists. That means the change of flux with respect to time is there, and based upon this Faraday came to a conclusion. So what Faraday related? Faraday related this change in the magnetic flux with the induced current, because this current was not there in this circuit because there is no source of current. You see, in this case I have not connected any external battery or something in this circuit so that a current should flow. So what actually we have done, this current is induced by itself. And why a current can be induced? If the current has to be induced in a circuit, then before that there must be an EMF which should be induced. So Faraday thought deeply about it, and somehow he established a relation between this change in magnetic flux and an EMF which got induced into the coil because of the movement of the magnet. Alright, so let's see how exactly Faraday framed his law. So there are two statements formally of the Faraday's law. You may join them together into a single statement or into a single paragraph maybe, but here for your betterment in understanding, uh, I have broken down in two different parts. So the first one goes like, whenever the magnetic flux linked with a coil changes, an EMF means electromotive force, is induced into the coil. The induced EMF lasts so long as the change in magnetic flux continues. So whenever you stop the magnet no longer moves, or the velocity of the magnet becomes zero. In that case, this EMF automatically stops. The value of this EMF is automatically brought down to zero. So that is why it is written that the EMF, or the induced EMF rather, lasts so long as the change in magnetic flux continues. Second point, the magnitude of EMF induced in a coil is directly proportional to the rate of change of magnetic flux linked with the coil. So that is why we can establish that this is the EMF E, which is equal to d phi upon dt. Basically Faraday came down to the statement that the induced EMF is directly proportional to the rate of change of the magnetic flux per unit time. He could not find whether there is a negative sign or not. By the way, now we know there is a negative sign, and this negative sign indicates that the induced EMF always opposes any change in magnetic flux. Now this statement will be clear whenever we go down to Lenz's law, because this statement is actually a consequence of the Lenz's law. So from Lenz's law only this negative sign appeared. Previously Faraday could not establish this. Alright. However, whenever we will solve numerical problems, we will always consider this negative sign and we will solve. So this is all about Faraday's law, that whenever the magnetic flux linked with the coil changes, an EMF is induced into the coil, and the EMF lasts so long as the change in magnetic flux continues, and the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux with respect to time. So this is in brief the statement of the Faraday's law. Now based upon this, let us see a numerical problem. So the first problem goes like this. It says the magnetic flux threading a coil changes from 12 into 10 to the power minus 3 Weber to 6 into 10 to the power minus 3 Weber. in 0.01 seconds, then calculate the induced EMF. So it's very simple. We know that E is equal to minus d phi dt, so which basically means phi 2 minus phi 1 divided by delta t. Delta t is the change in time, and according to the question, phi 1 is equal to 12 times 10 to the power minus 3 Weber. Phi 2 is 6 times 10 to the power minus 3 Weber. So this leads us to 6 minus 12 whole into 10 to the power minus 3 divided by 0.01 second. So if you solve it down, hopefully you should get an answer of 0.6 volts. So that is the magnitude of the EMF induced because of this particular change in the magnetic flux. All right. So this is problem 1. Let us go down to the next problem. The second problem is a little bit critical in understanding, so please concentrate. The following figure shows a conducting loop. So I'm talking about this particular loop. This is a loop. This is a closed loop near a long straight wire carrying current I. So this is the carrying straight wire. This is the straight wire which is carrying a current I. This I'm talking about. If the current increases continuously, if this current, by the way, this current is not static, this current increases continuously, means with respect to time you are suppose increasing this current, then find the direction of the induced current in the loop. So because of this current there will be a magnetic field, and because of that magnetic field the flux linked with this loop will change, and which will eventually create a current in this loop or set up a current in this loop. You have to find the direction of this current which is being set up in this loop. Alright, so this is basically the problem in front of us. So let's just once again draw this loop. So this is my loop. Alright, and here is the straight wire carrying the current I. Now the question is, let us first, I don't know what is the direction of the current in the loop. So let us first put a direction of the current. Let's consider this is the direction of the current, which should be, say this current be I prime, because this current is designated or denoted by I. So let's say the induced current be I prime. Alright, so if this is the situation, this is the direction of the current. This is, by the way, remember that this is an assumed direction. There is no such thing. If my theory matches with the Faraday's law, by considering this direction of the induced current, then I will say, okay, this is a correct direction. Otherwise, I said that this is not the correct direction, the current should be in opposite direction, something like that. So if this is the direction, then by right hand thumb rule, the area vector is going into the page of the paper. Into the page of the paper, what the right hand thumb rule says, suppose this is the thumb of a person. So in that case, if the current is going in this direction, the magnetic field points in this particular direction. That is what is the area. So if you just close your fingers to this direction, then your thumb will point into the page of this paper. That means to that side, this side basically. Alright, it's not the vertical direction I'm showing, I'm just showing it to be into the page of the paper. So that is why this cross symbol is there. Whenever we want to say that something is coming out of the plane of the paper, we put this symbol. And if sometime we want to say that okay, something is going into the page of the paper, we put this symbol. Okay, so this is into the paper, and this is out of the paper, out of the plane of the paper basically. Okay, these two symbols must be remembered. Alright, so fine, hopefully we have understood. So if this is the direction of the area which is going into the plane of the paper, then because of this current there will be a magnetic field which is going through this loop. We know if there is a straight wire carrying current I, then because of that there is a magnetic field. Now the interestingly see the magnetic field also going into the plane of the paper, so the direction of the magnetic field which crosses this loop is also going into the plane of the paper. So both the area vector ds and the magnetic field are going into the plane of the paper. All right. So what is the change of flux? Phi, that's equal to given by B dot ds. Now whenever this I changes with time, this magnetic field will also change, and consequently ultimately there will be rate of change of this flux. But interestingly, the B and ds both have the same direction. That means the angle made by B and ds, angle made between B and ds is equal to 0. So what you can write is that it is sort of BDS cos of 0, that is equal to 1, so it is BDS. All right, the product of the magnetic field and the area. So phi is positive. If phi is positive, if you take a d phi dt, that is also going to be greater than 0, or that means a positive quantity. All right, so this is greater than 0 or a positive quantity. Now d phi dt, if it is greater than 0 for this particular value of the current, then we are sort of violating the EMF, because what we know that the EMF induced should be opposite to the rate of change of magnetic flux. That means sorry, this should not be there, it's not a vector. The rate of change of magnetic flux should be negative of the EMF. So but considering the direction of this current, we have considered that rate of change of the magnetic flux is positive, so which is not a case, or which should not be a case according to Faraday's law. So we must consider the direction of this current in opposite direction. That means the real direction of the current will be this. All right, so it is opposite to what we initially assumed. So what basically we have followed an algorithm, like the algorithm is choose a direction, random direction of a current, and because of that, if your flux is coming positive or the rate of change of flux is coming positive, then you should change the direction of the current, because this is a direct consequence of the Faraday's law that electric field should be the negative rate of change of the magnetic flux. All right. So this is basically a very intuitive problem in a sense. Sometimes this kind of problem appears in examination, so you have to be a little bit careful, right? So I would like to end up with this particular thing. Next class we will understand Lenz's law in detail, but before that, these are the references. These 4 references are very important, and all of them are important. I mean, I cannot say that okay, you go through the first or second, which is more preferable. No, all of these 4 books I have gone through, and all are equally good. But my personal suggestion, if you ask, in that case I would say I will be following this and this mainly heavily, because of the numerical problems given in there. So you can have these books, these 3 books mainly, and if possible then the 4th one also. These are all recommended in your Guwahati University syllabus also, and we will be following these books mainly. So thank you for today. We will see you in the next class with Lenz's law. Thank you.